Last class we discussed how to find area underneath of a curve, and it's not really finding the area. We didn't find exact values, but we were able to approximate or estimate them by taking a curve and splitting it up into rectangles and then finding the area of all those rectangles and then just adding that together. Okay, now just to review some of the concepts here a little bit and talk about the major ideas that we came across toward the end of the class here. The first concept that we talked about was a situation where I gave an example of where I think we were going to drive for 3 hours. So we had a time component along this axis, and then up along this axis was some rate of change component. Okay? Or in other words, this was a derivative value along the side. Okay? And we decided that if we have this, whether this is a straight line or whether it's a rough curve, it doesn't really matter. If we find the area underneath of that curve, we decided that that area should equal the total change, okay, within an object. Whether we're talking, if this is a rate of change of distance, okay, like a speed, okay, then we figured out that the area underneath the curve represented the total change in distance that we were traveling over the course of 3 hours or whatever the problem was about. Okay? So the area underneath of a curve is a total change component, and that's the first major concept we talked about last time. Okay? The second concept was, well, what if this is not a very nice curve? Well, how do we estimate these values? Okay? Or what if we know this equation? How can we estimate the area underneath of that curve? And we decided that we should try to split this up into rectangles. Maybe split this up into 4 rectangles. Equal distances all the way along the x-axis down here. And then we draw heights either on the right side of the rectangle or the left side or the middle. We have our choice on those. But if I was doing a right-sided rectangles, I'd come over here and I'd draw a rectangle, the heights being on the right side, the heights being here on the right side, the heights being here on the right side, and so forth. And then we would just find the area of all those rectangles and add them up and say, well, this is going to be fairly close to the value underneath of the curve. Okay? Toward the end of class, we decided that an even better approach is to let a calculator do a lot of this work and split this up into even more rectangles. If we go up to 100 rectangles or 1,000 rectangles, we get an even better estimate. Okay? Now, I want to point something out here on the overhead. Okay? This is a very common definition in most calculus textbooks here. You'll see this total change concept right here. Okay? And this looks like a rather messy description of what total change is, but I'll kind of describe to you what this is saying here. A lot of the same thing I'm saying on the board. It's saying here we're coming in and we're saying this delta x is our change. This is our width of each of our rectangles. That was the thing that we could always factor out from the last class period, the 1/4. Okay? So we always factored out that change in x. F of x sub I, that's just saying the height of each of those rectangles. Okay? So we take the width times the height of each rectangle, and that gives us an area. Then what we do is we add up, this is a summation symbol, we add up all those areas together, and when we get to the end, okay, that gives us a total area for an answer. Now, what this part is saying is, now let's, instead of just picking 4 rectangles or 10 rectangles or 100 rectangles, let's let the number of rectangles go off to infinity. Let's just let's get it to be as many rectangles as we can ever come up with. And it says if we add up the area of all of those rectangles, as many as we can get, another way of calculating that, or another mathematical equivalence, is that this is the same thing as finding the area underneath that function as an antiderivative. Okay? So this is a big connection for us here. And the name we're going to give something like this here later on today, we're going to call this the fundamental theorem of calculus, or part of the fundamental theorem of calculus. This is one of the biggest breakthroughs that they found when they were developing this idea called calculus. As soon as they found out that if we add up a whole bunch of rectangles and just let this go off to infinity, if we use our ideas of limits and it is equal to this, well, that was a huge breakthrough. That allowed us to solve a lot more problems that they weren't able to solve before in a nice, efficient manner. Okay? So that's what this is. That's where this is leading here. Okay? Now, last time we did some examples where I gave you the function. And the example that I can think of is we did x squared. We had this x squared value in here, and we found the area from 0 to 1, I think. Okay. Today we're going to look at some situations where we do not know the equation of the function. Okay, so, and that's going to make more sense, because what this is really telling us is if we know the function, we probably don't want to solve the problem this way. We probably want to solve the equation this way. Okay? But if we do not know the function, then we don't have a choice. We have to fall back on those methods from last time. Okay? And so let me flip a couple pages here, and let's look at an example. Okay? Let's see here. Back it out a little bit. I'm going to leave the odd-numbered problem, and we'll work this even-numbered one here, this number 26. The question talks about a graph showing a concentration of alcohol in a bloodstream. Key thing that I want to point out here is that notice along the x-axis we have some time component as our independent variable, and up along the y-axis here, alcohol units per hour. So it is some type of a slope label or derivative type label. This is not just total units in your bloodstream, this is units per hour. Okay? And so that's a key thing to recognize. So in other words, if we were to come in and find the area underneath of this curve, that's how we would determine the total number of units in the bloodstream. Okay? So if we want to find a total value, when we're given a rate of change along the y-axis, we have to find the area underneath the curve. Okay? And what I want us to do is use this graph, and we're going to calculate R4 for this particular graph. We're going to find out the area underneath this curve with 4 rectangles, and the rectangles will be drawn on the right side. Okay? Now, I'll have to do a lot of pointing on this because I can't draw on the overhead screen here. But my first question is, what will be the width of those rectangles if we split this region up into four rectangles? It'll be a width of 2, correct, because we're trying to cover the total time of 8 hours. We're going to split this up into 4 equal time intervals, so we want 2 hours each. Okay, so the first time interval goes from 0 to 2, and then from 2 to 4, 4 to 6, 6 to 8. Okay, now, in the first time interval, what value am I going to use for my height? And I said we'll use the right side. So we're going to use the very end of the time interval to make our prediction on the units per hour for that whole time interval. Okay? So I'm going to come over here to 2. I'm going to go up here, and I see that the height at 2 is equal to 2. So my first setup on R4 is I have a width of 2, a time interval of 2, and a height of 2. Okay? Then I go to the next example. Okay? Well, now I'm going from time 2 to time 4. I still have let 2 hours elapse, but what do I use for the height on that time interval? Well, I use the height on the right side, which is at 4, and if we scroll up here, approximately how high? About 3.5. Okay? And remember, we don't have to be exact because this is only an estimate anyway. Okay? So we're just doing the best we can as an estimate. Okay? All right, next time interval goes from 4 to 6. Okay, what do I estimate the height to be on this one? 3.25. Probably 3.25. Yeah, seems pretty reasonable here. So we've got 2 hours going by, 3.25 for that time interval. And then what about for the last time interval from 6 to 8? Well, we come over to the right side, approximately 1 for the height on that one. Okay, and I can go through and add these all up and get an estimate of the total amount of alcohol in the bloodstream over these 8 hours. Now, obviously there are disadvantages to this estimate. The big advantage is it's a really rough estimate, and it gives us a pretty decent idea of how much blood alcohol is in the bloodstream. Okay? Disadvantage, though, is this. Okay? If we look at the time from 0 to 2, I picked the height of my rectangle to be on the right side here. Okay? Is this height of 2, is that a pretty good representation of this time interval from 0 to 2? No, I've picked the most extreme case. I've picked the right side of the rectangle. I picked the highest value within that whole time interval. So this estimate of 2 times 2 here is actually going to be as big of an estimate as I can. Now, this is the most alcohol in the bloodstream. This is a worst case scenario almost. Okay? If I come over here and look between 2 and 4, again, I did pretty much the same thing. I picked the highest value again. By doing the right side, I'm keep picking the highest values. Now, from 4 to 6, we ended up choosing this value. It's not the highest value this time because we have a peak right in the middle. So maybe this third interval, maybe I did a pretty decent job of picking a nice value that's somewhere between the highest and lowest. Okay? So there's sometimes, one more here, and then from 6 to 8, this time I actually picked which value? I actually picked the lowest value. So what kind of happens in these curves, sometimes you end up picking a value that's really too high. Sometimes you end up picking a value that's really too low, but we kind of hope that things average themselves out a little bit and give us a decent estimate of what's going on. Okay? All right. Now, we could do L4 for this as well, where I pick values on the left sides, but I won't write that one down. What might be the best estimate, though, when we're using graphs? Well, probably your best guess is usually use midpoints. Okay? I do want to write this one out. Let's go ahead and write out M4 for this example. Okay? Just as an estimate. Okay? Again, I only want to go to 4 rectangles, so I split this up into 2-hour increments. And in the first 2-hour increment, what am I estimating the alcohol units per hour to be? Well, the midpoint of this first interval is what? 1 hour. And if I go up along 1 hour, I'm estimating the value to be what? 1. Okay? And that seems to be a pretty good estimate, because if I look just from 0 to 2, I know it's not perfectly linear, but it's fairly close to linear here. And I'm picking the value right in the middle of that line. So that'd be almost a perfect estimate there. Okay? All right, if I go from 2 to 4, the middle of the time interval is 3. What do I estimate the height to be? Okay, 3. And I know you can see it's a little bit lower than 3, but go ahead and just pick 3. I mean, it's an estimate anyway. There's no reason to pick 2.9, okay, because we're just estimating anyway. So for that 2-hour time interval, I'm going to say that the value is 3. Okay, what about from 4 to 6? Okay, yeah, this one's 5. If I go up here, yeah, it's definitely a little bit more than 3.5. 3.75 I think is a pretty good idea here. And then for the last time interval, I would do what? I would go look at 7, and 7 has a value of about what? About 2.5, right. Okay. So I can go ahead and find this value, and if I want to use midpoints, this will probably give me a decent estimate. Okay. Now, if I want to get a better estimate, what could I change over here to get me a better estimate? More rectangles. Sure, I could go just 1-hour time intervals, and I could have 8 rectangles. Okay. The advantage of 8 rectangles, it gives you a better estimate. The disadvantage is instead of adding 4 things together, you're now adding 8 things together. So you have to decide, well, how many things do I want to add together to make it worth my time for this estimate? Okay. All right, so any questions with using graphs? It's just a little different than functions. We just have to manually look at the graph and pick out those y values. Whereas last time we had functions where we would sub in x coordinates to get these y values right here. Okay, that was our difference. All right, the other example that I want to look at here is a table of values. And let's see which one. I was going to work 35 here. Bit here. Okay, it says the speed of a particle in a test lab was noted every second for 3 seconds. So they're marking down not where the particle is at, but they're marking the speed of the particle. So they have some way of measuring its velocity. Okay? The results are shown in the table. Use left endpoints and then right endpoints to estimate the total distance the particle moved. Okay? Again, key things that I noticed from here, this is a table with time along the x-axis and speed along the y-axis. And the question is asking for a total distance. So that tells me that's why I want to find the area underneath of this curve. Okay? Those are the key clues, the key words that I noticed in this. All right. First thing they said to do was find L4. So I'll just go ahead and leave what I've got up here. Okay? So the first time interval goes from 0 to 1. So how much time has gone by? Yeah, just 1 second, right? From 0 to 1. So in the first second, what am I going to use for the speed of that first second? I'm going to use the left side of that time interval, so I'm going to use 0, which is 10 seconds, right? Or not 10 seconds, 10 feet per second. Okay, I'm going to use the speed of 10. Okay, what value am I going to use for the second time interval between 1 and 2 seconds? 6.5, right. I'm going to use the left side of each one. Okay, so this is from 0 to 1, so I used 0. This is from 1 to 2, so I used 1. Okay, now I go to the next one here. Okay, for the third time interval, I'm going to use what? I'm going to use 6. Let's see, what am I... The results are shown in the following. I guess it really didn't say L4, did it? This is really what? How many rectangles, or how many time intervals do I have here? This is just L3, right? Okay, I just looked at my table wrong. I saw 4 numbers along the top, but this is really only going to have 3 time intervals, because 0 to 1 is 1, then 1 to 2, and then 2 to 3. Right, okay, so it's just really L3. Sorry about that. Okay. Okay, so that's L3. If I go through and add those together, I can come up with a result. Okay, now, what if we were to go through and calculate R sub 3? What if we were to use the right sides of these time intervals? Instead of using the beginning, let's use the end of the time interval. Okay, so what would this look like? 1 times 6.5, 1 times 6, and 5.5, sure. Okay, and I could add all those together. This would give me the estimate on the right side. Okay, now, probably the best thing to do in this scenario, even though they don't ask for it in this problem, probably the best thing to do is we realize, well, in the first second, 10 is probably not the best estimator, because it looks like the speed just continues to decrease. So by picking 10, I'm picking the highest speed in that whole time interval. Okay? The left, or the right estimate is probably also not the best, because if I pick 6.5, I'm probably picking the lowest speed in that whole time interval. Okay? So lefts and rights are okay because we have nice numbers for them, but one of them is probably going to give too big of a distance, one's probably going to give too small of a distance. What's probably our best move from here? Probably just average the two, right? So my guess is that if we really want a good estimate here, let's just average L3 and R3. And that value should give a decent estimate of what we're looking for here, total distance. Okay. All right, any questions with graphs or tables? In some ways, the graphs and tables are actually easier than the functions.
What's an example of where we wouldn't use midpoint or average? Just left and right.
And a good time to use either just left or right would be a lot of the functions that we've been working with here. Like, for example, on this one, the numbers just continued to go down the whole time. And so that's why left and right weren't as good, because it was kind of a linear or maybe a quadratic. It was just going down the whole time. So a lot of the situations I've been working have been either going down the whole time or up the whole time. That's why left and right aren't as good. Okay? When you get situations where you have lots of curves, then picking values on the left and right, then it gives better estimates, because one time it's too big, the next time it's too small, and then it kind of works itself out. Okay? Yeah, so that's a better situation. Okay? Anything else? All right. We're going to change directions here a little bit now, and we're going to go back to what we were talking about last time with functions. Okay? And we're going to look at solving things like this. Now, I introduced this notation to you last time. This is saying that we are interested in finding the area underneath the curve x squared. So I go ahead and draw x squared. Okay? We want to find the area from 0 to 1 on this graph. Okay? So here's 0, and over here is 1. So the area we're interested in is all this area underneath the curve here. And we estimated this last time. We decided I think it was close to 0.33 or 0.34, something like that. Okay? Well, if we have a function, or at least with some nice functions like this one, we can find this value exactly using calculus. Okay? Now, I have been referring to this a lot as an antiderivative. Okay? Another word that can be used that I think I've thrown in once or twice, we also call this an integral. Integral being the opposite of a derivative, just like an antiderivative is the opposite of a derivative. Okay? This type of integral that we will be working here today, because we have boundaries, we're going just from 0 to 1, this is going to be called a definite integral, because we have definite boundaries on it. We're just going from 0 to 1 and we're stopping at 1. Okay? So if you ever see something talking about a definite integral, it's just the same thing as an antiderivative. Okay? All right, now here's how this process is going to work. And the name given to this process was called the fundamental theorem of calculus, one of the most important ideas that they discovered in the development of this course of calculus here. Okay? They said if you want to solve this just with nice algebraic tools and calculus tools, here's what you do. Step 1 is just take the antiderivative. Just ignore the 0 and 1. Take the antiderivative of this function. Okay? And what is the antiderivative of x squared? X to the third divided by 3. Sure. Okay? This one has a nice antiderivative, so we'll be able to solve it. Okay? Some functions will not have nice antiderivatives. That's when we'll have to fall back on what we just talked about, solving it by hand with rectangles. Okay? But if it has a nice antiderivative, we can solve this very easily. Okay? Now, the way that we write this is we go ahead and take the antiderivative, and then we just put a line over here to the right, just some type of a bar, and we say that we're now going to substitute in the values x equals 0 and x equals 1. Okay? All right. If I sub in the value of 1, whoops, there should be a plus constant on the end there. I forgot to write that. Okay? If I sub in a value of 1 into this equation, what do I get for an answer? 1/3 plus some constant, right? We don't know what the constant is, but you're going to see here in a minute it doesn't matter. Okay? So I just subbed in 1/3 plus the constant. Okay? Now, what if I sub in 0 into this function? What do I get? 0 plus the constant, right? Okay? And what they decided, or what they figured out in the development of this, they said that if you sub in the first number and you sub in the second number and you subtract those values from each other, that will tell you the area from 0 to 1. Okay? So if we go through and simplify this, what's the final answer here? Yeah, it's just 1/3, and the reason it's just 1/3, here we've got a plus constant, here we've got a minus constant, so those constants actually cancel each other off, and we just end up with 1/3 minus 0, which happens to be 1/3. Okay? And so the total area underneath this curve from 0 to 1 is exactly 1/3. Now, our estimates the other day kind of confirmed that we were close. We said somewhere between 0.33 and 0.34. Well, this is somewhere between 33 and 34. Okay? And this is exactly the value. So if we have a function that has a nice antiderivative, we don't need to go to rectangles. We can just use this process, and it works very nicely for us. Okay? All right, so there's one example of using antiderivatives to calculate these values. Now let's look at a few more examples. What if we are interested in knowing this right here? The area from 0 to 2 of 5x squared minus 4x plus 2. So this time we have a quadratic function, just like we had a quadratic here a little bit ago. And we want to find the area from 0 to 2 on this graph. Okay? All right, step 1 is just take the antiderivative. So go ahead and tell me, what's the antiderivative here? 5 just stays there. Antiderivative of x squared is what? X to the third divided by 3. Okay? Second one, the negative 4 just stays there. Antiderivative of x squared divided by 2. And the antiderivative of 2 is what? 2x. Okay? And then a plus constant on the end. So I just go through and take the antiderivative, and then I sub in the values 0 and 2. So I just put a little line out here. I say I'm going to sub in 0 and 2. Okay? All right, now we start subbing in these values. Okay, if I sub in 2 here, this will become 8. 8 times 5 is 40. And for right now, I'm just going to leave it as a fraction. 40 divided by 3. The second one, if I sub in 2, looks like 16 divided by 2, which is 8. And then a plus 2 times 2, which is 4, and then plus a constant. Okay? So that's what I get when I sub in 2 in for all the x's. Remember, don't sub it in for the c, just for all the x's. Okay? Then I subtract what I get when I sub in 0. And the nice thing is, if I sub in 0 into all these, I just get what? A whole bunch of zeros. So 0 plus a constant. Sure. Okay? Now, when I clean all this up, what do you notice happens with the constants? Constants always cancel off. Okay? And so what we do in math, we get a little bit lazy eventually, okay, in the fact that we just realize that no matter what this constant is, it's always going to have a plus constant here, and it's going to have a minus constant over here. They're always going to cancel off. So we don't necessarily, when we're doing this process, we usually don't even have to write the plus constant in there, because we just remember every time it's going to cancel off anyway, so it's not going to really matter. Okay? So if you write it in here, that's fine. If you leave it off, that's not going to be a problem either. Okay? All right, then we just go through and we just calculate this value here. 40 over 3 minus, looks like minus 4. If I put those two together, 4 is the same thing as 12 over 3. And so this looks like the answer of 28 divided by 3. Okay? So if I was to go through and graph this function, 5x squared minus 4x plus 2, and I was to shade the region under the graph from 0 to 2, that area would be equal to 28 divided by 3. So just a little bit more than 9 units of area underneath that curve. Okay? Okay, next example. Area from 0 to 4, negative 3x to the 3 halves plus x to the 1 half dx. All right, we just have to be a little more careful this time because we have this negative sign in here. Okay? My first recommendation would probably be take that negative sign through the parentheses. Just eliminate that problem right away. Okay, so I'm going to rewrite this as negative 3 and negative square root of x. Okay, then we don't have to worry about that, losing that negative sign anywhere. Okay, start by taking the antiderivative. So the negative 3 stays there. What's the antiderivative of this? X to the what? 5 halves. X to 5 halves divided by 5 halves. Sure. Okay. Minus antiderivative of x to the 1 half. X to the, okay. This is 0.5, so if we add a full unit, it becomes 1.5, and then we divide by 1.5, right. And again, I don't really care if you turn these into fractions or if you turn these into decimals. Okay, and that's why I kind of did one of each, because it's the same answer either way. Okay, so I really don't, that's a personal preference, whichever one you're more comfortable with. Okay? Really, there's a plus constant on the end here, but we don't need to write it because it'll eventually go away anyway. Okay? And then I decide now I want to calculate the value from x equals 0 to x equals 4. Okay? I start subbing in those values. Okay? Well, what do I get when I sub in 4 here? Square root of 4 is 2. 2 to the 5th, let's see, 4, 8, 16, 32. Okay? So it'll be negative 3 times 32 divided by 2.5. We'll have to punch that in. I don't think that's a very nice number here. Okay? And then minus what I get when I sub in 4 here. Well, 4 to the 1.5. That'd be the square root of 4, which is 2. 2 to the 3rd is 8. And so this is 8 divided by 1.5. Again, I don't think it's a very nice number here, so we'll probably have to punch it in the calculator. Okay? All right, that's what I get when I sub in 4. Now, minus what I get when I sub in 0. Well, 0 to any power is what? That's 0. 0 to this power is 0, so I just get a big 0 over here on this spot. Now, all the examples we've done so far, whenever we've subbed in 0, everything has zeroed out. That won't always be the case, but it's fairly common that it is. Okay, so just be careful. If you ever get some things in there like e's, if you ever sub in at 0, e to the 0 is not 0. So just to be a little careful. Okay, but a lot of times those things will just cancel off. Okay, and you can calculate this and that'll be your answer. Now, the thing that I want to point out with this one though, if you do calculate this, what type of number do we get on this one? This is a negative number. And so the question then becomes, okay, what does it mean if I take the area underneath of a curve and I get a negative value? Okay, good. Just means that the area happens to be below the axis. Okay, so I don't know what this graph looks like, but if I just draw a rough picture here, okay, maybe my graph looks something like this. And I'm finding the area from 0 to 4, so the area that I'm finding is just this area right down here. And so if I get a negative 10 for an answer, it just means there's 10 units of area here. It's just that they're 10 units and they're all below the x-axis. So that's all it means if you ever get a negative answer down here. You still have area, but it's just all below the axis. Okay? All right, very good. Let's see. I want to jump down to this question right here. Let's do the area under 4 minus x. And I'm making this one up on the fly. I need to get it to work right here. And let's go from 0 to 8 on 4 minus x. Okay? All right, now let's see what happens with this situation here. Area from 0 to 8 to 4 minus x. Okay? All right, what's my antiderivative? Antiderivative of 4 is 4x. Antiderivative of x, x squared divided by 2. Okay? And then I would have a plus constant on the end. Then I want to sub in the values of x equals 0 and x equals 8. Okay? All right, what do I get when I sub in 8? Well, 4 times 8 is 32. And then over here, 8 squared is 64. 64 divided by 2 is what? 32. Okay? So when I sub in 8, I get 32 minus 32, so it zeroes out. Okay? What do I get when I sub in 0? I just get 0. So what's my final answer for this problem? 0. Okay? Now, what does this mean? I got a total area of 0. Now, that doesn't quite make sense, though, because we know, let's just look at the graph of this. If I graph 4 minus x, that means I have a y-intercept of 4, and my slope is negative 1. So my graph is doing something like this. Okay? Now, my question to you is this. Okay? Where is 8 on this graph? Well, first of all, where's this point? This is 4, right? Because if I just keep going down by 1, it's going to take me 4 units to get there. So this is 4, so 8 is somewhere over here. Okay? What do you think it means if we get an area of 0 when we do an antiderivative? See if anyone can figure this out from my graph here. And the key thing in this graph is that 4 is right in the middle. Go ahead, Mike.
Because from 4 to 8 is below the x-axis,
Mhm.
so it's negative, so it cancels out.
Exactly. That's exactly what happened. Okay? If we were to find the area from 0 to 4, and I don't know what this number is, I'm just going to make one up here. Let's just say it's 10. If this is 10, what's this area have to be over here? Negative 10, because we have nice symmetry here. These areas are exactly the same. So this one was 10, and this one was negative 10, and when I added those together, I came out to be 0. Okay? So that's what happens when you get an answer of 0 on one of these antiderivative problems. It just means you have as much area above the axis as you do below the axis. It doesn't mean that there's 0 units of area. It just means that we have the same amount above and below the axis. You know, if this is a physical sciences problem, we have a balance here, okay, because we have a total area of 0, okay, or a net area of 0, put it that way, okay? All right, so that's all this means. And the same situation could be applied back to this problem. I don't know what this graph looks like here. I don't know if this whole graph is underneath the axis. But if I get a negative answer, it means that more of the graph is underneath the axis than there is above the axis. You know, maybe it's one of those situations. Okay? You know, if this answer happens to be negative 10, okay, and I'm finding the area here, I would be finding this area plus this area plus this area. Okay? So maybe this is negative 12, and maybe this is negative 4. Okay, so that's negative 16. If this area was 6 up here, negative 16 plus 6 could net to be negative 10. So I may have a situation like this where I've got some above the axis and some below, but when I add all those together, I come out with a negative number. Okay, so that's all this is telling us, just telling us the total net amount of change or net area that we come up with. Okay? Now, there are different types of questions, though, and I want to bring this one up here. Let's see. Well, it's just 4 minus x squared. And we're going from 0 to 4 on this thing, on 4 minus x squared. But this time, instead of just saying to calculate this, the question says find the total area. Okay. Now, if the question over here said find the total area, do we want positive and negative areas to cancel each other off? No. We want to find a total area. That means we want to find all of this area, and then we want to add that to all of this area over here. In other words, if I get a negative answer, I want to take its absolute value and make it positive. So if this was 10 and 10, I would end up with a total area of 20. Okay? All right. So now, if we come over here to 4 minus x squared, and the question is find the total area, the first thing that you want to do is graph this function and figure out where's the negatives and the positive areas at. Okay? So let's go ahead and graph this. We realize this is a parabola that's got a peak at 4 and it's decreasing. You know, if you graph it on your calculator, here's what you would see, is you'd see this inverted parabola at 4. Okay? I want the area from 0 to 4. Well, I know where 0's at. That's right here. I'm not quite sure where 4 is at, though. Okay? First question that I might want to know is, well, where's this intercept over here? What value could I sub in for x to come out at 0? I could sub in 2, right? If I sub in a 2 here, that zeroes it out. So this is over here at 2, so I'm going to exaggerate this a little bit here. So somewhere over here is x equals 4. Okay? So I've got region here that's going to be calculated, and I've got region here that needs to be calculated. If I just do the 0 to 4 antiderivative, that's going to take this and it's going to subtract this area down here. Well, that's not what I want if I want the total area. So what I need to do is I actually need to break this down into 2 separate antiderivative problems. Okay, what's the first area that I'm interested in solving? I'd want to go from 0 to 2, right? Because this is all positive area. So if I change this and go from 0 to 2 and calculate that value, that will tell me this area up here underneath what appears to be underneath that parabola there. Okay? Then if I add on the area from 2 to 4 of all of this, okay, 4 minus x squared. Now, here's the only thing though. I want to add this area plus this area to get my total area. But what type of number is this going to be down here? It's going to be negative because we see that this is all below the axis here. So what I need to do is whenever I get my answer, I'm going to need to take the absolute value of that number. So if I get a negative 5 over here for this answer, I need to make that a positive 5 before I add it on. Okay? So that's the only thing here. We don't necessarily need to solve this problem because it's not much different than the other ones. But just recognize that if they want a total area in a problem, okay, then we need to take all negative areas and make them positive. And then to do that, we have to split the problem up into multiple sections to be able to calculate this. Okay? If they don't say anything about total area, then they're probably just more interested in what we call the net area. You know, positive minus negative areas added together. Okay? All right. Where are we at now? What if we've got an example like this? Area from negative 1 to 0, y times 2y squared minus 3 to the 5th, dy. All right, we want to find the area from negative 1 to 0 on this function. What am I going to have to use to be able to calculate this antiderivative? What's different about this setup than some of the other ones we've been doing? Okay, one of the things that's different, this one starts at negative 1 and goes to 0. Right, okay? So we're actually finding area to the left of 0, okay? Now, we don't know if it's positive or negative area yet, but that is a difference. We're working on the left side as opposed to the right side. Okay? So that's one thing. What about the actual function here itself? What do you notice about this? Okay? Well, this is a product, right? We've got some variable y times another function with another variable y in it. Okay? Do we have a way to undo a product rule like this? Well, not really, but what did we talk about last time as sometimes a way to work this? We talked about this idea of substitution, right? Okay? And so the question becomes, can I make this a substitution problem? Can I make it an antiderivative with substitution? Okay? Well, let's take a look at it here. What do you think the substitution would probably be here? Yeah, let's let u equal all the stuff in parentheses. Okay? So 2y squared minus 3. And then what's du? What's the derivative of this? 4y dy, right? Okay. Now, does this piece, is it close to the other part of the product? And the answer is yes, it's very close. This is y, this is 4y. We can do some algebra to this to make this match up exactly. So substitution is going to work pretty well here on this example. Okay. What will this look like when we substitute it over? Okay? All of this will become what? U to the 5th, right? Okay, that's what we tried to clean that up and make it a little easier to work with here. So I've substituted for all of this. Okay? The thing I have not substituted yet for is y dy. But how could I do some algebra to this to get y dy by itself? Divide off the 4, right? If I divide both sides by 4, okay, now I've got y dy is exactly the same thing as du divided by 4. So I can put my du over here, And somewhere I can put a division by 4. I can write it as a fraction 1/4. Okay? And does this antiderivative look more manageable than the first one? And I hope the answer is yes, because it really is. Okay? Now, notice I haven't done anything with the boundaries yet. Okay? These boundaries are values to sub in for y. So do I want to keep -1 and 0 down here? And the answer is no, because when I solve this problem, I'm going to have u's in the problem. Okay? So what we have to do on these substitutions is, when we change the variable over to u's, we also must change the boundaries over to values of u. Okay? So what I'm going to do is this. I'll start with the top here. I'm going to take this 0, which is really a y-coordinate, and sub it into this equation. If I sub in 0 for y, what do I get? I get u equals -3. So I'm going to replace this 0 with a -3. Because I have changed over to u's, I need to change my boundaries over to u's as well. Okay? What about if I plug in -1 down here? -1 squared is 1. 2 minus 3 is -1. Now, this is coincidence that this number was -1 and this was -1. I mean, that happens sometimes in functions. You plug in a value and you get out the same output. Okay? But we still had to do that because we needed to change these numbers over to u coordinates instead of leaving them on y's. Okay? Now I can go ahead and finish off this problem. What's the antiderivative of 1/4 u to the 5th? Well, it'll be 1/4 u to the 6th divided by 6. And now I can substitute in these new numbers, -3 and -1, and I'll come up with my result. Okay? Notice what else happened along this process. It looked, here we were going from -1 to 0. Okay? Here it almost seems like we're going backwards. We're going from -1 to -3. So it's almost like we're going from right to left on this problem. Okay? But, does it matter? Okay? If we're calculating an area, and I go from left to right, and I go from right to left, does it still capture the same area? The answer is yes. Okay? So we still go ahead and we don't have to worry about that being switched. Okay? And from here, it's just a matter of subbing in the numbers and finishing off the problem. Okay? All right. We'll see you Friday.